So now we'll get started on the notes. The equation up at the top is the one that I just derived in the summary video. So it just says that if you want to take the integral of u dv, you can do that by just taking u times v minus the integral of v du. And before you worry about this too much, just wait until we get through a few examples, and I think then you'll see how this can be applied in practice. But the way that I want you to think about this is if you want to compute an integral where one of the terms, or really one of the factors, is u, and that's hard to integrate, then what you can do is you can use this integration by parts formula to turn the left side here into this right side. And notice that the right side involves an integral that has du instead of u. So this allows us to sort of differentiate one of the factors inside of the integral. So ordinarily, whenever we're choosing what u is and what dv is, we're going to be looking at what factor inside of the integral would become nicer if I were allowed to differentiate it. So in general, we want to choose u so that du is nice and simple. And then we want to choose dv so that it's something that we can integrate, because we need to be able to find v from dv. And a general rule of thumb that we have for choosing u is you want u to be something whose derivative is nicer. So if I have a logarithmic function, then whenever I take a derivative, it will become significantly nicer. So this, whenever I take a derivative, is going to become 1 over x, which is just a power of x. And similarly, algebraic functions get nicer whenever we take a derivative because their power diminishes. So if I take the derivative of 2x, it's just going to become a constant, which is 2, and that's a little easier to deal with. Exponential functions don't really become much simpler whenever we differentiate them. So that's why they're last on our list of selections for u. So we want u to be something that is simplified whenever you take a derivative of it. At the bottom here, there's a list of little rules that you might want to use when selecting u. I'm not going to worry about this too much. This is just a set of restrictions that you might want to consider when performing this sort of integral, but I think it'll be better for us to just dive right into the examples. So here we're told what u and dv should be. So we want to be integrating 6x times ln of 3x dx. And here the idea is that we're going to rewrite this as the integral of ln of 3x times 6x times dx. And this part, the ln, I'm going to call that u. Because remember, we're trying to choose u to be something whose derivative is nicer. And we don't like integrating ln. Instead, we would prefer to integrate something like its derivative. So that'll be our u. Once you choose u, the rest of the integral has to be dv, or I should say the rest of the integrand. So the rest of this is going to be our dv. And that's what we were told in the prompt. Now remember, the integration by parts formula says that the integral of u dv is equal to u times v minus the integral of v du. So I want to be computing this integral of u dv. And to do that, I'm going to try replacing it with this right-hand side and see if we can evaluate the right-hand side instead. Now what I like to do is, as soon as you've chosen u and dv, I like to make a little table that tells you what u and du are, and it also tells you what v and dv are. That way we can just plug them into this formula up here at the top. So u was chosen. We know that u is equal to ln of 3x. And now du would be the derivative of this, or really I should say the differential of this with respect to x. So if you take the derivative of ln of 3x, that would be, you put the 3x down below and its derivative up top, so this would be a 3 over 3x, which simplifies to 1 over x. And really, it's okay to put the differential here, so that would be times a dx if you'd like. And then similarly, here we started with dv, so we know that dv needs to be 6x dx. To get v, we would integrate this. So if I integrated 6x dx, then what I would get is a 3x squared, because I would add 1 to the power on that x, and then I would divide by the new power. In other words, divide that 6 by 2. So this is what we get as our u, v, du, and dv. And now we're going to take the integral that we started with, which was the integral of u dv, and I'm going to substitute in the right-hand side instead. So I'm going to rewrite this as u times v minus the integral of v du. And in this case, because we've already computed all of these things, we can just plug them in. So this would be u times v minus the integral of v du. So this would be v du. And du was 1 over x dx. So this is uv minus the integral of v du. And now we can clean this up a little bit. So this is ln of 3x times 3x squared minus the integral of, if I clean up this integrand, I have an x squared divided by an x. So those would cancel, and I would just get the integral of 3x dx. And this will end up being ln of 3x times 3x squared minus the integral of 3x. If you integrate 3x, you would add 1 to the power on x and divide by the new power. So that would be a 3x squared over 2. And then, because we just did an antiderivative, we should have a plus c here. So this is what we get as the original, or I should say as the antiderivative of this original expression here. And if you want to check answers, you can still check answers here. All you need to do is take the derivative of what's in the box here. And if you take the derivative of that and you find that it agrees with the integrand that you started with, then you did it correctly. So that's what we do for integration by parts. The goal is usually in integration by parts to try finding some part of your integral that would be simplified if you could take a derivative. And in this case, the thing that would be most simplified is that logarithm. So we called that logarithm u, and then the rest of it we called dv, and then we applied the integration by parts formula. So remember this little shorthand up here, that we want to first try choosing u to be a logarithmic function if it exists, because those become especially nice when you take a derivative. And then second, we'll choose them to be algebraic functions, because at least those diminish in power as you take derivatives. And then lastly, we'll choose exponential functions, which usually don't get that much nicer whenever you take a derivative. Okay, so let's just do some more examples of these, because I think as we do more examples, you'll start to get more comfortable with it. So staring at this, maybe it would be a good idea for you to just look at these two factors and decide which of those would actually become nicer if we could take a derivative. And whichever of those you think would become nicer, that's probably going to be your u. So the tricky thing, I think, in integration by parts problems is right there at the beginning, deciding which one of these should be u and which one of these is dv. So here we have an algebraic function, which is x, times an exponential function. And the algebraic functions are higher priority for our u's. So I would let u equal x, and that means that the rest of this stuff has to be dv. So this is going to be my u, and this is going to be dv. So if u is equal to x, then the differential of u is just the differential of x. So du is equal to dx. And dv is the rest of our integrand. So this would be e to the 4x dx. Now for v, you need to integrate to get from dv to v. So we would integrate the 4x dx. If I integrate 4x dx, the integral there would be e to the 4x divided by 4. So if you need to do some scratch work to compute that integral, then you can. So you could do this with a u substitution if you'd like. Now this is a little bit confusing because unfortunately I've already used the letter u. So maybe I'll use the letter w here. So w is going to equal 4x. Then that means that dw is equal to 4dx And that means that that dx in our original integral could be replaced with a dw over 4. And then that integral that we're trying to compute to find v would be the integral of e to the w times a dw over 4. If I just replace e to the 4x with e to the w and dx with dw over 4. And this would be 1/4 of the integral of e to the w dw, which is just e to the w. And that means in terms of our original variable, this would be 1/4 of e to the 4x, or in other words, e to the 4x over 4. So that's how I got v. Now, what I like to do is if you're integrating something like, so this is just sort of a side comment, if you're integrating something like e to the 7x dx, something to remember about exponentials is that if you are differentiating an exponential like this, then the exponential term will stay the same, and then you'll multiply by the derivative of that inside function. So this would be 7 times e to the 7x. If you wanted to undo something like that, then the opposite, or the integral, would be to take the original exponential and then divide by that 7 rather than multiplying by 7. So that can be a good shortcut to just remember that if you're integrating e to a constant times x, then it will just be the same thing, but then divide by that constant, which is the opposite of what you do when you differentiate. There you're just multiplying by the constant. So that's how I got my answer so quickly, but it's always okay to just do the scratch work that I did over here on the side, if that's helpful. Okay, so now we have our u, our v, du, and dv. So we can get started with the integration by parts formula. Remember that integration by parts says that the integral of u dv is equal to uv minus the integral of v du. So that's the formula we want to be using. We started with the integral of u dv, and this is then u times v, which is x times e to the 4x over 4, minus the integral of v du. So this would be minus the integral of e to the 4x over 4 du, and du here is just dx. So this is v du. So this would be x times e to the 4x over 4 minus, we can factor out that 1/4 if we want. So this would be 1/4 times e to the 4x, the integral of e to the 4x dx. And then we've already integrated e to the 4x dx, but remember you can integrate something like this by just dividing by that constant. So this would be 1/4 times e to the 4x divided by 4. That's what we found the integral of e to the 4x dx to be. Now, I do want to note that this only works, the division by 4 thing, or the division by this constant, that only works if the exponent is a constant times x. If the exponent is anything more complicated than that, then you can't use this simple multiplication or division rule. Then you would need to use some of the other techniques we've talked about, like this one, integration by parts, or something like a u substitution. And because we just took an antiderivative, I'm going to add c. But notice that now we're done integrating. So we've now found the antiderivative of this expression that we started with. So this would be x times e to the 4x over 4 minus e to the 4x over 16 plus c. So that's our antiderivative. And if you wanted to check your answer here, then what you would do is you would take the thing in the box and you would take its derivative, and you would hope that that matches x times e to the 4x. Because the antiderivative of x times e to the 4x should differentiate to give you x times e to the 4x. So if you take the derivative of this thing, you can check that it actually is x times e to the 4x, and that means we've successfully integrated what we wanted to. So we'll keep going with more practice in the next video, but if you want to get a bit of a head start, before you start the next video, think about what the choice of u and what the choice of dv should be in this example. because here in this example you have an algebraic function times a logarithmic function. And if you really want to get a head start, try to compute all 4 of the things that were in that box that we started with, like u, du, and v and dv. So see if you can compute all of those before you start the next video.